Hi everybody, I'm Liu Yantong. Today I will introduce a cutting-edge topic, bioinformatics in brain-computer interfaces. My presentation will cover four main sections. I will start by explaining what brain-computer interfaces are. Then I will move on to how they actually work. After that, I will dive into the role of bioinformatics in BCIs, and finally, applications of BCIs. First, what is brain-computer interfaces? It is a link between mind and a machine that allows users to control devices using their brain activity. Some BCIs can even send information back to the brain. Based on the signal processing method, BCIs can be divided into two categories, synchronous BCI and asynchronous BCI. The former collect and analyze signals within fixed time windows, while the latter performs real-time monitoring. So now you might be wondering, how do BCIs actually work? Their workflow can be summarized by the word mind, which stands for measure, interpret, encode, and deploy. This process begins by measuring brain activity with specific devices. Then we interpret and encode the data using machine learning algorithms. Ultimately, the decoded commands are deployed to control an external machine or a computer. Now, let's take a closer look at the workflow of BCI, starting with the measurement step. As shown in the table on the right, there are several methods for acquiring brain signals. These methods can be broadly classified into invasive and non-invasive. Invasive approaches involve surgically implanting recording devices directly into the brain. They offer high-quality signals but carry significant health risks. Non-invasive methods, which are performed entirely outside the brain, are much safer, but the signals tend to be noisier and require advanced techniques to achieve high resolution. Additionally, the type of brain activity measured varies between methods. For example, EEG captures electrophysiological activity. In contrast, fMRI detects the hemodynamic response, which reflects changes in blood flow and oxygenation related to neural activity. Let's look at two typical methods, one non-invasive and one invasive. The non-invasive method is EEG. It captures microvolt level electrical signals generated by neurons. These signals are categorized into rhythmic frequency bands, each carrying different meanings. For instance, delta waves are linked to deep sleep, while beta waves are related to motor control. However, because the signals must pass through the skull and scalp, EEG data can be quite noisy and low in amplitude. The invasive method is ECOG. This approach delivers much cleaner and stronger signals, including alpha, beta, and gamma waves produced during motor action. Now we have recorded our data. We've got to interpret what it means and decode it into information that computer can use. Generally, this is done by machine learning. For target words, we repeatedly record the brain activity associated with it. This builds a dataset containing multiple words, with each word represented across many trails. After undergoing steps, such as filtering and feature extraction, the data will be encoded into computer-readable formats and used for machine learning training. Once the model is trained, if the brain thinks of a word that was included in the training set, the system may predict that word with high accuracy. For example, if the subject thinks of the word A, The system learns the brain signal from the language area for A through multiple trials and uncover its unique patterns of activity. Later, after training, when the system detects a similar pattern, it can predict that the subject is thinking of the word A. Finally, the decoded intention is put into action, either to control a computer or a machine. In the left image, you can see a user playing a video game using only brain signals. On the right, a BCI-driven assistive device helps an individual with limited mobility regain finger movement. This is how intention becomes interaction. Bioinformatics also plays a critical role in brain-computer interfaces. Gene editing technologies, such as CRISPR, can be used to modify neural circuits, fine-tuning the function to enhance signal clarity and control. Also, genes fundamentally shape brain signals by determining key neuronal properties, including the types of neurotransmitter and receptor, as well as the composition of ion channels. These genetic factors directly influence neuronal excitability and signal transmission efficiency, which in turn affect the precision and reliability of signal in BCI systems. Inspired by biological evolution, the genetic algorithm was originally widely applied in the field of bioinformatics. In current BCI research, GA has been adopted as an automated method to extract an optimal set of relevant features from neural signals. And that's not the only overlap. Many other techniques for pulling out features or classifying data are also shared between bioinformatics and BCI. This shows how much these two fields overlap. Tools and ideas move back and forth, pushing both areas forward together. Today, brain-computer interfaces have found many real-world applications. One of the most impactful is motor neural prosthetics. This technology enables individuals with disabilities to regain control of their body. Moreover, BCIs can enhance communication, information search, and entertainment. The first image shows two individuals typing and sending messages using only brain signals. The following two images demonstrate how BCIs enables users to operate search engines and software applications directly with their minds. Here are some references. Thank you for your listening.